Good morning all. This is Dr. D. Khalander Basha, working as Associate Professor in Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today we are going to discuss the interfacing devices with 8051. Under this we are going to discuss digital to analog converter as well as analog to digital conversion under the course microprocessor and microcontrollers. The slides are prepared by referring the textbook The 8051 Microcontroller by A.K. Ray, Kenneth Ayala, publication Singer's Learning. So interfacing is a technique that have been developed and being used to solve many composite problems in circuit designing with appropriate features, reliability, availability, cost, power consumption, size, weight, and so on. So to facilitate multiple features with the simple circuits, microcontroller is interfaced with the devices such as ADC, DAC, stepper motor, keypad, LCD display, like this, so on. So today we are going to discuss how we have to interface a ADC as well as a DAC with a 8051 microcontroller. So conversion between the analog and digital worlds require the use of integrated circuits that have been designed to interface with computers. So highly intelligent converters are commercially available that all have the following essential characteristics, like a parallel data bus, which may be tri-state and 8-bit size, and control bus, which is like to enable chip select or read write logic, read RPG, acknowledgement, status signals. This we can do. So the choice the designer must make is whether to use the converter as a RAM memory location connected to memory buses or as I/O devices connected to ports. So a generic R2R type digital to analog converter based on several commercial models is connected to port 1 and port 3 of 8051 microcontroller as shown in the figure. So the port 1 furnishes the digital byte to be converted to analog waveform. Port 3 controls the conversion process. So whatever the digital value which we want to convert into analog output, that we are going to be provided on port 1, which is of 8-bit size. Two control signals we are going to use for controlling the DTA conversion. So the digital to analog converter program generates 100 Hz sine wave using a 8-bit converter. Here the 166 decimal samples are stored in a lookup table and feed to the converter at a rate 1 sample for every 6 microseconds. So the lookup table is pointed to the external ROM, which is pointed by DPTR, and R1 is used to count the samples. So numbers, if you have specified, that will indicate the number of cycles. So now we will see the program where we are going to convert the digital to analog conversion, which is going to generate a analog waveform with making use of lookup table. So first we will enable the chip select of the converter. So for that, here we have selected the chip select will be connected to P3.20. So as it is active low signals, we have to pass this P3.20 as 0. So for that, first we are writing a clear port 3.2. The purpose of this one is to enable the chip select. So once we executed here, the CS pin goes to 0. Next, as the conversion values are stored in a table, the address of the table will be stored in DPTR with the base address. So move DPTR comma hash table, which is going to get the base address of the table into DPTR. Next here, move R1, comma, hash 0A6H. This is for initializing the R1 register with 16060 because as per problem statement, so how many samples we are stored in the lookup table is 166 samples. So for that one, we are going to be load the count into R1 register. So first we are going to be fetch the R1 value into accumulator, that is offset value of the table. Next, move a comma at the rate of dptr. So as dptr is holding the address of table and offset value is provided with a, so we are going to get the samples into accumulator. So where we can use move a comma at the rate dptr plus a. Next, the samples are sent to port 1 for conversion. So here port 1 is connected for sending the samples. The control signals are given on port 3. So once we are given a sample for digital to analog conversion, it is going to generate the equivalent analog waveform. So once this conversion is done, then we are going to write signal enable. So here write signal is connected to P3.3 and this write signal is act to low signal. So we have to make it is clear signal. So for that we will use the instruction clear P3.3. So once the write signal is given, immediately we will make inactive by writing as set B write 3.3. So whenever we pass the digital equivalent, immediately we make a write signal is active and disable it. Next, the number of samples which are stored in R1 register, as one sample is given for conversion, we go for decrementing the R1 register. If it is non-zero, go to the next level. So where we are going to be pass the next sample. Next, S jump, repeat. So now here, once the next sample is given, where we have to pass is, here we are going to write the next label. It is going to be fetched for the repetition. Next, for repeat, we can start from the beginning. Next, the lookup table begins here. A cosine wave is chosen to make the table readable. So the first 83 samples cover the waveform maximum to 1 less than 0. The next 83 samples covers the waveform from 0 to maximum. So 83 samples per half cycle means a sample every 2.17 degrees. So the lookup table will look like this. So in first entry, we will write as 00. Next entry is FF, FE, FEH, FDH, FDH. So like this, when we are done, so we are going to be approximately near to 90 degrees. So like this, in the table, we are going to have total 166 samples that will be converted. Next, we will see A to D conversion. So the easiest A to D converters are the flash type ADCs, which makes the conversion based upon the array of internal comparator. So in this flash type ADC, we are going to have a number of comparators, where these comparators are again will be connected to priority encoder. Depending upon the comparison, it is going to produce the equivalent digital output. So what this comparator will do is, for each comparator, one of the signal is analog signal. The second input is given as a reference voltages. So R1, R2, R3 like this, you are going to have reference. Next. So the conversion is very fast. Typically is less than 1 microsecond. Thus, the converter can be told to start and the digital equivalent of the input analog value will be read 1 or 2 instructions later. So modern successive approximation register, where we use in successive approximation method, it will converts do not lag for behind. However, with conversion time is in the 2 to 4 microsecond range for 8-bit case. So an example using a generic flash converter is shown in figure, where we are using the port 1. It is for reading the byte values of the input analog voltage, and port 3 it is used for generating control signals in 8051 microcontroller. So once we are applied the analog signal, which will be given to pin number 1 of flash A to D converter. So whatever the analog signal which we are giving here, that it will be converted. After conversion, the digital equivalent will be sent on the lines port 1. As it is 8-bit size, we can write this bit pattern from port 1.0 to port 1.7 bit. So now this port will be configured as output port. So for controlling this flash A to D, we are going to have a write signal, a read signal, and chip select. So a conversion is started by pulsing the write signal to low because it is active low signal. Then the data is ready, bringing the read line low. So the following example involves the digitizing of analog every 100 microseconds until 1000 samples have been stored in the external RAM. First, we are going to equate that 4000 H, where your program is going to store at 4000 H. Next, here a delay in a DJNZ loop, it is for 87 microseconds, assuming this delay subroutine is existing. Next, this 43H, it is for high byte of the ending address, whereas this N2, which is E8, is the low byte of the ending address. The program will start at 000H location. So first we are going to be store the address of the RAM where the samples are to be stored into DPTR. Next, we want to make the chip select as active. If you observe the pin, the chip select is active low signal. That means we have to send the chip select value as a 0. So for which pin we have to send this one as 0 is P3.2. So P3.2 we have to clear. When we clear, it indicates this chip, which is flash A to D, will be active. So for making it, we are going to write clear P3.2. So the purpose of this one is, it is to make the CS signal active. So when CS signal is active, means it is a active low signals, we have to write as 0, then the ADC will be active or selected. Next, for generating the write pulse, so if you observe, the write pulse is connected to P3.3. Here also, the write signal is active low signal, so we have to pass the bit value for P3.3 is 0. So for that, we can make a clear P3.3. So this clear P3.2 will make the CS signal as active. Clear P3.3 will be used as the read signal is write signal. Write signal is 0. Next, to clear or inactivate this write signal, we are going to be pass set P3.3. So now here we assumed P3.3 is connected to write bar. So once we are given 0, immediately we will make as 1. So one pulse we are making active, immediately we are making disable. So for that we go for set P3.3. Next we have to generate the read pulse. Now in the figure, the read pulse is connected. The read pulse is connected to P3.4. And if you observe, this read pulse is active low signal. So the value on 0 will make the read signal as active. So for that, we are going to be write the instruction is clear P3.4. So when we make clear P3.4, it will generate a read pulse. As the read pulse is a active low signals, so when you make the read pulse as 0, then reading process will be starts. Next, for getting the data after conversion, the data will be getting from this A to D to port 1. So we want to read this data of port 1 into accumulator. So for that, we will write the instruction move A comma port 1. So this will copy the converted a digital value for the given analog signal which is existing at the port 1 into accumulator. So then we'll make set PP 3.4 because once the read is done, then we are making the read signal as inactive by making a read bar is equivalent to 1 as a read signal is connected to port the 3.4 bit. So we will set that particular port bit by using the instruction set PP 3.4, which will make the read signal as end pulse. So what is end means? Inactivating the read pulse. As it is a active low signal, when you pass the value as 1, then it is going to be inactive state. 0 means it is active state, 1 means inactive state. So once we remove the read pulse, then the data which we are copied from port 1 into the accumulator, this we want to load into external memory. So the external RAM address already it is having in a DPTR. As it is a external signal, external memory, we are going to use the instruction is MOVX, which is for copying the data to the external memory, or from the external memory, we are going to use the instruction is MOVX. So MOVX, the external memory address is in DPTR. The value which we want to store into that memory location is in accumulator. So we use the instruction MOVX at the rate of DPTR comma A. So whatever the converted value which we are read into accumulator from the port A, that value we are going to be stored into the external RAM. So once one data which is of 8-bit after conversion we are going to be stored in the external memory, we have to go to the next memory location. So for that we go for incrementing the DPTR. Next, the DPH value we are going to be load into accumulator. Then we are going to check whether it is reached the end one. So initially we are declared end one, which is the higher byte end one, higher byte of the ending address. So first we will compare it. If it is not done, so for what we are doing here, compare. What we are comparing? DPH value, because the DPTR, which is a 16-bit register, out of these 16 bits, the lower bits will be there in DPL, and the higher byte is in DPH. So first we will check whether the higher byte is reached or not. Once the higher byte is reached, then we go for checking lower byte. So here we are going for comparing. What we are comparing? The DPH value which was stored into accumulator, that value we are compared with end one, which is the higher byte. When these two are same, that means the accumulator content is equivalent to end address or higher order address, then the 0 flag will be set to 1. If these two are not equal, then the Z flag is equivalent to 0. So we want to repeat this one until the higher byte is reached. So when these two are not same, so go for wait state. Next, the DPTL will be loaded into accumulator. Again, we will compare with the accumulator contents with the lower byte of the end location. Then if it is not same, then go for wait. So once these two are done, we are going to be finished by using simple done. So in the wait, what we are doing is move R1 comma hash delay. So this is a program for a delay program. Next, here DJ inject every time a decrement this count. If it is non-zero, go to here only. That means this will be treated depending upon the count which you have specified in R1 register. So the delay which you are providing here, it is for by providing the delay value is 87 microseconds. Next, once this one is done, then you go to SJump next. So where we have SJump next here. Again it will be go for right pulse. Then it will set right pulse. The remaining process will be takes place. When the conversion is done, simply we go for resetting into the same instruction. Then we will end with the indirect to dot end. Next program is demonstrate the ALP to generate a sawtooth waveform using 8051 microcontroller. So sawtooth waveform means we want to generate a digital signal where it is going to vary from 00 to FF in the increment manner. Once it reaches to FF, it will be decremented from FF to 00. This is for only one pulse. If you want multiple pulses, again we need to go for sending from 00 to FF, FF to 00. Again one more pulse, 0 to FF, FF to 00. So like this we are going to generate a series of sawtooth waveforms. So for this, we require only one port, some port 1 or port 0 or port 2 you can take, which will be given the analog signals. This is a DAC, digital signals to digital to analog converter. Whatever the pattern which you are sending, that it will be converted. So first we will pass 00, some waveform it will generate. Whenever we pass 01, whenever we pass 02, 03, like this it is going to generate until FF. Every time we will compare whether this value which we are going to be load into a register or accumulator, we are going to check until FF. Once it is FF, go for decrement. So first we will clear the accumulator. Then the first one we are going to generate from 00 to 01 to FF. So increment A. And here the digital to analog converter is connected to port 2. So whatever the accumulator contents are there, that we will send for port 2 for conversion. So we will send the accumulator contents to port 2. Now the data will be sent for the conversion. Then we are going to compare the accumulator content with FF because it has to range from 0 to FF. So once it is FF, go to up. After each and every pulse, you can provide some delay, then SJump up. So this is for generating ramp signal actually. The sawtooth we want means again from FF to 00. Here we will write few more instructions. So this will generate a ramp signal. If I want a sawtooth waveform, we will write the instructions like this. First clear accumulator, then increment accumulator. Some label will give for up. Move port 2 comma accumulator contents. Now it will compare CJNA. Until what point we are going to compare this accumulator content with FFH. If it is not done, go for sending the data until FF is reached. So once FF is reached, then we go for decrementing. So here we will write a decrement accumulator. Why we are going for decrementing? Because from 00 to FF, once it is raised, for generating sawtooth waveform, again we have to come from FF to 00. For that decrement A. So whatever the value which we are getting, that we will send again to port A for conversion. Again we will compare 00. So CJNA accumulator with hash 00H and goes to up to, where up to is the next level which you can provide. So this up is going to, this I'll write as down instead of up to, because we are changing from FF to 00 now. So this up label, it is for generating a ramp signal from 00 to FF in increasing manner. Whereas this down will generate a sawtooth waveform, the second part, where it is ranging from FF to 00. So when you execute this program, it is going to generate one RAM. If I want a repeated one, so then you can go for sjump. So it will start again generating the memory files. Right. This is for RAM generation. This is for sawtooth. So clear accumulator, increment accumulator, move port 2, A, CJNE accumulator content with FFH. It is done for up. Then if you want to go for downside, then you go for decrementing accumulator, move port 2, accumulator, CJNE. Now we'll compare with 00H. Else you go to down, where down will be placed here. So this entire program will generate one pulse. If I want a repeated pulse, then I can go for sjump, again start from up. Right. So this is a program for generation of ramp as well as sawtooth waveform. Suppose if I want to generate a square wave, how we can generate a square wave? Here also first we'll clear accumulator. That accumulator contents will be passed to, here I'll write a square wave, which is a small program. So first we'll clear accumulator. This accumulator contents values will be passed to port 2. Then we'll call delay. So if your delay program is existing within 8-bit wide, you can go for using sjump. If it is 11 bits, ajump. If it is 16-bit displacement, long jump, anything like that. So wait for some delay. So this will generate a square wave with 0. Then we want to get 1. For getting that, go for move accumulator, FFH. So 0, 0 I am taking for logic 0, FF I am taking for logic. So then again we will send move port 2, A. Then we will call the subroutine delay. So now this program will generate only one pulse. If I want repeated pulse, sjump, some label. I'll write loop 1, where I have to place loop 1 at the beginning. Now this program will generate a square wave. So this is 3 programs for ramp generation, sawtooth waveform generation, and triangular wave generation. This is triangular wave. Ramp or sawtooth wave same. So thank you. In this session, we have discussed the interfacing of DAC and ADC to 8051 microcontroller, and we have seen few programs corresponding to the conversions. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.